99% of software engineers cannot solve Google's favorite interview question, edit distance. We're given two strings, word1 and word2, and we want to return the minimum number of operations to convert word1 to word2. We have the following three operations permitted on a word. 1, we can insert a character. 2, we can delete a character, as well as 3, we can replace a character in word1. So for example, if we have word1 as horse and word2 as ROS, let's go over our three options at a time. First, we can insert a character at the front of the H in horse. Namely, in this case, we would insert an R to match with the R in ROS of word2. After that, we just need to match horse with OS. So second, we can delete a character, namely the H in horse, and then focus on matching the rest, ORSE, with ROS. We can also replace a character, replacing the H in horse to an R to match the R in ROS, and then we just need to match the remaining ORSE with OS. Notice how this matching process is recursive. For each operation we apply, we will end up needing to recursively match a different remaining suffix of word1 and word2. This inspires a dynamic programming approach, where dp of I, j represents the minimum number of operations to match the suffix of word1 starting at index I with the suffix of word2 starting at index j to the end. Let's handle the base cases. If we are both at the end of word1 and word2, we're done. The two strings are fully matched and we need a total of 0 operations to match two empty strings. If we are at the end of word1 but not word2, we just need to insert the remaining length of the suffix of word2 to match. We cannot do any other operation since we have no words left in word1. And if we are at the end of word2 but not word1, it's the opposite. We just need to delete the remaining length of the suffix of word1 to match the empty word2. We cannot do any other operation since we have no characters left in word2 to match with. Now we are guaranteed to have a character to compare with in word1 and word2. So let's think about how we can represent the three operations. Recall in our example, if we wanted to insert a new character, we add it in the front of index I in word1 to match with index j in word2. So we matched with index j, but we still haven't used the original index I. So we need to recurse on dp of I, j plus 1. So in our example, right, if we insert an R at the front of word1 to match with the R in word2, we still need to match the entire HRR with OS in word2. And we add 1 since this takes one operation. For a delete, we simply remove the index I from word1 and try to match the remaining strings. So this is dp I plus 1, j. In our example, we would delete the H and then just try to match ORSE with ROS. And we add 1 since this takes one operation. Now for a replace, it depends on if word1I and word2j already match. If they already match, we don't need to replace. We can just match and recurse on the remaining suffixes. Recurse on dp of I plus 1, j plus 1. This is like in example 1, if imagine horse started with an R, then we can just match that and then recurse on ORSE and OS. If they don't already match, then we need to use one operation to replace it, and then recurse on dp of I plus 1, j plus 1. So in our example, this is changing the H into an R, right, and then matching ORSE with OS. So we simply want to take the minimum of these three choices as our answer. And so our final answer is simply dp of 0, 0, since this gives the entire matching of word1 and word2. Follow for more Leetcode.